Okay, we have a very pretty question from electrochemistry, that is from the application of Colros's law, where we are provided with a weak monobasic acid which is undergoing 5% dissociation, right, in zero point 0.0 mole per liter solution. So basically in the beginning we are provided with alpha, so alpha is equal to 5% and that becomes equal to 0.05, right, in fraction, where the concentration is also given, which is 0.01 mole per liter or 0.01 molar, right. Then the limiting molar conductivity at infinite dilution, that is lambda m infinity, is also given. So we have to go for the conductivity of 0.05 molar solution of an acid. So we have to calculate at this concentration, we have to calculate the conductivity, which is basically molar conductance. Remember this, the conductivity at this concentration. So we have to calculate conductivity at this concentration, which is not the kappa, but which is actually the lambda m. Since concentration is provided to you, so we have to calculate lambda m, right? So this was the basis to construct the question. Okay, now we can approach the question. The only thing that you need to understand is alpha, which is 5% given in your question, is at a concentration 0.01. Now we know that when concentration changes, if you remember this graph, when we plot a graph between a lambda m c versus under root c, right? So whenever we changes the concentration, if there is change in concentration for weak electrolyte, then lambda m must changes, and if lambda m changes, then there must be a change in alpha as well. The degree of dissociation, the extent of dissociation also changes. So we can calculate lambda m at the concentration 0.05 only if we know alpha at that point, particularly at that point. So we need to calculate alpha first. This alpha which is given in your question is at concentration 0.01, so we have to calculate alpha at concentration 0.05. Now the relation that I can use is, we know that this dissociation constant, that is k d or ki, or whatever you can write down, k alpha as well, is equal to c alpha square, right? And from this we can get alpha is equal to under root of kd upon c. Now we have to compare two concentrations, so we can calculate the other alpha from comparing the two equations. Now we know that this alpha 1 upon alpha 2, just make two equations. Now kd is common in two equations, so it will get cancelled out, so we'll only compare with the concentrations. Now since concentration is inversely proportional, so we'll get c2 upon c1, right? So this is the relation where the two concentrations are given, and if one alpha is given, we can calculate another alpha. So alpha 1 upon alpha 2 will be equal to under root of c2 upon c1. Now we'll put the values. Now the alpha 1 is given, which is 0.05 divided by the alpha 2, which we have to calculate, and will be equal to under root of the c2, the concentration 2 is given 0.05 divided by the initial concentration, which is 0.01. So we can directly calculate the extent of dissociation at this much concentration. Now we get 0.05 divided by alpha 2 is equal to, we'll get under root 5, right? And this under root 5 is equal to 2.23. Now alpha 2 will be equal to, just transporting, rearranging this equation, so we'll have 0.05 divided by 2.23. So this will be equal to 0.0224, right? So this is alpha 2. Now you can see that when concentration increases, this alpha decreases, obviously, since in the beginning the concentration was 0.01 and alpha was 0.05, like 5%. Now when the concentration increases, the alpha will decrease, obviously, so we get 0.0024. Now at this alpha, for this concentration 0.05, we got the alpha without using kd, even though the second alternative method to calculate this alpha was making use of this dissociation or ionization constant, but without going through that ionization constant, we can directly calculate alpha 2. Now when we get the alpha, now by using the equation, we can calculate lambda mc. Now we know that alpha is equal to lambda m at given concentration upon lambda m at infinite dilution, right? So we have to calculate lambda m at concentration 0.05. This will be equal to alpha into lambda m at infinite dilution. Now alpha, which we just calculated is 0.0224 multiply by the lambda infinity. The lambda infinity is provided in our question, which is 4 into 10 raised to minus 2. So this is 4 into 10 raised to minus 2. So this comes out to be 0.089 multiplied by 10 raised to minus 2, or to round off to 1 digits, we can get 8.9 into 10 raised to minus 4 mole later inverse. Sorry, this is lambda m, na, right? So we'll have ohm inverse centimeter square and mole inverse, right? So this will be the final answer.